Hi, my name is Ferine. Happy New Year. I'm a supply chain professional. Today's session is about AI literacy, not coding, not tools, but understand how AI actually works in a very practical use case, lead time prediction. We all hear about the benefits of AI, but for AI literacy, the important questions are, how is AI different from traditional methods? How does it really predict? And what needs to be in place for it to predict well? The goal of this session is to help you understand what AI is actually doing, how lead time prediction works, and what conditions must exist for AI to work reliably. This is about how to think about AI, not how to code AI. Traditionally, we rely on static master data, historical average, or padding buffers. All three assume lead time is stable or uncertainty can be absorbed manually. These methods work until variability became the norm. Traditional lead time method worked until the world changed. Geopolitical events like tariffs, natural disasters, sudden demand shifts, and labor disruptions now happen more frequently. As a result, lead time changes often, variability is high, and manual updates are simply too slow. What we need today are predictions that adjust weekly, sometimes daily, reflect current conditions, and respond faster than humans updating master data. AI works better now because we have more data, more compute, accessible platforms, and models built specially for supply chain problems. The environment finally caught up with the idea. The biggest difference between traditional planning and AI isn't accuracy, it's how lead time is understood. Let's compare how traditional planning and AI look at the same problem. Traditionally, lead time is a static estimate, one number we reuse. AI treats lead time as a dynamic and PO specific. Instead of ignoring variability, AI models it explicitly. Instead of limited context, it incorporates seasonality, lane, quantity, and transport mode. Updates are no longer manual. Predictions are rescored as conditions change. Most importantly, risks are made visible and measurable, allowing planners to move from gut feel to evidence-based trust. The goal isn't to replace planners, it's to give them better signals. In theory, lead time is PO to receipt. In reality, suppliers behave differently each time. AI focuses on predicting what actually happened under today's conditions, which directly improves safety stock and service levels. One common misconception is that AI predicts a single fixed supply lead time. It doesn't. Instead, AI predicts three related things. First, an expected lead time. For example, this PO will likely take 47 days. Second, a lead time distribution, such as P50 at 45 days and P90 at 62 days. P50 means half of the past POs arrive in 45 days or less. P90 means we need to plan for 62 days if we want 90% confidence. When I say past, I mean historical POs with similar conditions, not all POs. Third, AI can predict delay risk. For example, a 35% chance this PO will miss the promised date. These predictions are extremely useful for expediting and exception management. One important reminder, these are probabilities, not guarantees. This slide shows the difference very clearly. Traditionally, we plan with a single number, supplier X equals 30 days. What this hides is seasonality, logistics constraints, and most importantly, risk and variability. With AI, we look at the same supplier in context. For supplier X in Q4 via sea freight, the most likely lead time is 35 days. And if we want a 90% confidence, we plan for 48 days. The supplier didn't change, the visibility did. Lead time becomes contextual, risk is explicit, and planning shifts from fixed numbers to a probability-based decisions. Let's briefly look at how AI actually learns at a very high level. The first step is defining a very clear learning question. For lead time prediction, the question is simple. How many days does it take from PO release to GR goods receipt? That number, the actual lead time, becomes the label the model learns from. Each data row represents one historical PO line or shipment. So the model doesn't learn from opinion or rules. It learns from what actually happened. Once the data is prepared, AI looks for patterns across thousands of POs. It starts to see things that are very hard for humans to quantify consistently, like suppliers behaving differently by season or certain lanes slowing down during monsoon periods. It also learns that larger order quantities increase variability, that promised lead times can be optimistic, and that new suppliers or new products are usually more volatile. These patterns exist in the data, but they are extremely difficult to capture with simple average or static rules. Once the model has learned patterns from history, we move to prediction. For a new PO raised today, AI outputs an expected lead time and a confidence range. For example, a P90 means 90% of similar past POs arrive in 62 days or less. This is where the value shows up. These predictions fit directly into MRP, safety stock calculations, and expediting thresholds. Instead of reacting late, planners can act earlier based on quantified risk, not gut feel. You don't need to know the algorithms in detail, but it helps to know what kind of thinking they represent. First, regression models. Think of these as smarter average. They are fast and explainable, but they struggle when the world isn't linear, which is most supply chains. Second, classification models don't predict days at all. They simply answer, will this PO likely be late or on time? Finally, tree-based models, which are the most common in practice. They work like decision trees. If this supplier on this lane in this season, then lead time behaves differently. That's why supply chains like them. They handle messy data, capture interactions, and are explainable enough to trust. This is the sweet spot for most companies. Before choosing any AI model, there are two prerequisites that matter far more than algorithms. First is business clarity. You need to be clear on whether this model replaces the ERP lead time or act as a risk signal. And most importantly, what action actually changes when the lead time increases. For example, if predicted lead time exceeds P90, does the buyer review the PO? If delay risk goes above 40%, does logistics step in? Without clear actions, even a good model creates noise. The second prerequisite is data readiness, and this decides success or failure. Timestamps are non-negotiable, such as PO release date, actual GR date, and consistent calendar logic. Garbage timestamps leads to garbage models. Context also matters, such as supplier, lane, transport mode, and Incoterms. Without context, the model is effectively blind. Finally, the gap between promise and actual lead time is extremely valuable. It reveals optimism bias and helps the model learn where risk really comes from. If you're missing any of this, your model won't work. Then fix the data first. Let me be blunt. Data readiness is a go, no-go game. It's not a checklist you can ignore. Step 1. Agree on the lead time definition. This sounds basic, but I have seen projects fail here. You must agree on the start point. Is it PO release, PO approval, or ASN? And the end point, is it first GR, final good receipt, or put away? What about partial receipt? Do you include them or exclude them? Are you using calendar days or working days? If there's no agreement across procurement, logistics, and planning, stop here, don't proceed. Step 2, minimum data required. At the PO line level, you need PO number and line, supplier ID, PO release date, GR date, and quantity order and received. One important reminder, poor data quality doesn't just reduce accuracy, it creates false confidence, which is far more dangerous in decision making. At this stage, we are not talking about advanced AI. We are talking about basic discipline. The first check is completeness. If PO release dates or goods receipt dates are missing, the model has no concept of time. That's why timestamps are the first thing to fix. Everything else comes later. Next is accuracy. What matters is that the GR recorded in the system reflects what physically arrived. If receipts are posted late or corrected in batches, the model learns artificial delays, not real ones. Then comes consistency. The same supplier, Incoterms, transport mode, and time zone must mean the same thing everywhere. If master data isn't standardized, the model sees noise instead of patterns. Finally, uniqueness. Duplicate PO lines or receipts create fake history. This must be removed before training. Otherwise, the model will confidently learn the wrong behavior. Beyond basic data quality, there are three checks that strongly influence whether AI gives realistic answers. First is timeliness. If receipts are posted days or weeks after goods physically arrive, the model learns delays that never actually happen. This creates artificial risk in the predictions. The second check is representativeness. We need to ask whether history reflects real operating conditions, including peak seasons, disruptions, and shutdowns. If we only train on good periods, the model becomes overly optimistic and systematically underestimate risk. The model isn't wrong, the history is incomplete. The third check is variability. AI only adds value when lead time actually behaves differently under different conditions. If lead time is always tightly clustered, simple rules are enough. But when we see seasonal or multimodal behavior, that is where AI delivers the most value. When teams ask me where to start, my answer is always the same. Don't fix everything at once. Start with the foundations. If timestamps are wrong or lead time isn't clearly defined, nothing else matters. These issues distort every downstream calculation and must be addressed first. Once the bases are stable, move to the high-value improvements. This is where consistency in supplier and logistics master data starts to unlock insights. The gap between promise and actual dates is especially valuable. It tells you where risk is systematically underestimated. Everything else can wait. External signals and advanced milestones are useful, but they only add value after the core data is trustworthy. AI doesn't reward ambition, it rewards discipline. Here is your go, no-go checklist. You are ready for AI lead time prediction if you can check all these boxes. If you can't check all these boxes, here is my recommendation. Pause the AI project, fix your data and process first. This isn't a failure. Fixing lead time data quality is already a supply chain maturity win, even before AI. You have better visibility, better reporting, and a stronger foundation when you do implement AI. I want to leave you with one final thought, especially for leadership. AI does not fix bad data. AI makes the bad data louder, faster, and more convincing. It will sound authentic, but in fact is systematically wrong. The good news is, fixing lead time data quality is a win on its own. Even without AI, you will have better visibility, better decision making, and stronger operational control. So I would suggest, do not chase AI because it's trendy. Build the foundation first, get your data right, define your processes, and then when you are ready, AI will amplify your capabilities. Before we close, I want to give you a quick preview of what comes next in AI literacy. First, how do we know when a model starts breaking? For example, when prediction accuracy drops or error starts increasing. Second, how do we use AI responsibly and ethically, including transparency, bias, and knowing when humans must stay in control? These topics are just as important as building the model itself. If you have questions or reflections, please drop them in the YouTube comments. I will be checking in and continue the conversation there. For more specific discussions, feel free to reach me through email. I've also shared my LinkedIn link and QR code on the screen. Do connect. I'm always happy to exchange ideas. I look forward to staying connected and hearing about your journey as you explore AI in your work. All the best. See you.